Welcome. Let us see another aspect of multiple driving forces. In this case, we are going to look at simultaneous temperature gradient and velocity gradient. Okay. This we haven't. This is the first time we are looking at temperature, I suppose, as one of the gradients in a combined situation in this course. So, we look at temperature gradient and velocity gradient. We would, as we have done many times in this course, we would look at a specific problem that would give you the context in which to look at these principles. And of course, these principles are general, they can be used anywhere where they are relevant. Let us consider this problem. A protein solution needs to be heated as a part of a certain analysis at small scales, a standard situation. You have a lot of lab on a chip kind of situation, analysis on a chip. The micro device used for the analysis uses a comparatively long horizontal metal tube of a small diameter, and the electrically heated tube wall heats the solution that passes through it in laminar flow. Okay. We already seen, since the diameter is so small, rho v d by mu for a given rho given d, for given rho given mu and the given solution, given liquid, that is, since the d is very small and the usual conditions are that v is also small, then you have laminar flow conditions there. Okay. They are going to flow in cylindrical layers. The heat flux at the tube wall can be assumed constant, which is mentioned. Find the temperature as a function of distance along the tube. Okay. We are interested in how the temperature changes as a function of distance along the tube. Okay. Again, this is a steady state situation. It's all set up. There are no changes with time that we are looking at, I suppose. Yeah, I think it's steady state. We'll see. Okay. What I'd suggest is pause the video here, go through the problem statement and internalize the situation in your mind's eye, okay, or make a mental picture of what is going on here. Can you do that? Hopefully now you have a better mental picture of what is happening. You have a thin cylindrical tube, metal tube, through which a protein solution is passing, and it is being heated at the cylindrical surface, and we would like to know the variation of temperature with axial distance. Here Vr is 0, there is no radial flow, it's all axial flow z. V theta is 0, of course, and q theta is 0. Okay. There is no heat that is being supplied like this, there is only a radial flux of heat. Let us assume constancy of physical properties and neglect viscous dissipation, negligible compared to the heating effects. Okay. Because we are heating here, the energies involved in this due to heating would be much larger compared to the energies involved due to viscous dissipation, because the viscosity, laminar flow viscosity, and so on and so forth. Okay. So, we are going to neglect viscous dissipation in comparison to the heating effects here. So, from the relevant tables, I am sure by now you are comfortable in using those tables, referring to those tables. Okay. I do not expect any of you to memorize any of those equations there. From the relevant tables in the earlier chapters, and I would like you to find out which tables. Okay. Pause the video here. This is the situation. Go back and find out which tables are relevant. Okay. We had tables for mass conservation, we had the continuity equation, we had tables for momentum conservation, equation of motion, we had tables for the charge, the energy conservation or heat energy equation, right, and also for charge conservation. Don't worry about charge here. We're not looking at charged aspects here as yet. For now, we have already spent a good amount of time on charged aspects. Here, don't worry about the charge associated. Look at the other three aspects and see which tables are relevant. Okay. You must be able to do this quickly now. Pause the video here, go and check, please. You would have found the equation of continuity is certainly valid, right? So, equation of continuity comes down to dou v z dou z equals 0. Okay. There is nothing else that is there. You go and check, you go and cancel the terms, check. You would get only dou v z dou z equals 0. Let us call this equation 6.3-1. Let me also tell you that the equation of motion is relevant. Pause the video here, choose the appropriate equation, cancel out the irrelevant terms, and can you tell me what you get? You would have gotten rho Vz dou Vz dou z, that is the only term that will remain on this side, equals minus dou p dou z plus mu 1 by r dou dou r r dou Vz dou r, this term remains, plus your dou squared Vz dou z squared, this term remains, the axial diffusion aspect remains. Okay. So, this is equation 6.3-2. Okay, rest of the terms will cancel out. In addition, equation of energy is certainly relevant. Okay, we are looking at energy being used for heating the protein solution. So, you have, if you consider the corresponding equation, okay, and I'd let you do in your own time, and then if you cancel out the irrelevant terms, these are the only terms that will remain. Rho Cv hat Vz dou t dou z equals k 1 by r dou dou r r dou t dou r plus dou squared t dou z squared plus mu dou Vz dou r squared. Okay. Note that we are concerned with the temperature variation along the axial direction. That is what we are looking for. Okay. So, you need to choose equations that are relevant from that point of view first and then cancel the terms. So, if you choose them and do this, you would get 6.3-3. Okay. So, all these are simultaneously valid. You have equation of continuity, equation of motion, equation of energy, right. So, only equation of charge has been left out mercifully. Okay. The you need to simultaneously solve these, right, to get the solution, because all these conditions, all these conservations are simultaneously valid. We have written the conservations in a form that will be useful. Therefore, if you solve them, you will get something that we are usually looking for. And in this case, we are looking for the temperature variation along the axial direction. Okay. So, if you simultaneously solve this, how do you go about doing this? I will show you one way of doing that. Okay, this is fine. This is all coming together, does not matter. So, we know dou Vz dou z equals 0 from the equation of continuity, and therefore, the derivative of that is also going to be 0. Okay. The derivative of 0 is 0, dou z of dou Vz dou z equals 0, and therefore, this equation of motion, dou squared Vz dou z squared is going to go to 0. Therefore, these terms will remain here, and therefore, you have dou p dou z equals mu 1 by r dou dou r r dou Vz dou r. Okay. And we have already seen this equation in the momentum flux section. Therefore, we have already seen, we have already solved, and therefore, we can directly take the solution from that. It is exactly the same equation, exactly the same boundary conditions, and so on. Okay. So, Vz equals P naught minus Pl r squared by 4 mu L 1 minus r by r squared, the classic parabolic velocity profile. Also note that we had derived this for a flow down a vertical pipe. In the momentum flux chapter, we had done that, and that we did to generalize something. We could set the capital P as the pressure, and the rho g h could be taken along with that to call it a capital P, and that was one of the reasons, that was the main reason why we consider vertical pipe. You could generalize that. Okay. So, it kind of nicely fits into all the mathematical manipulations that we do, whether you do this or do this, and we can combine these terms, therefore, that term does not appear separately, and so on and so forth. It simplified the solution. What I would like you to do is pause the video here, derive the equation for a horizontal tube for the case of laminar flow, and you need to check what happens there. Check whether this capital P reduces down to just the pressure alone. Okay. Please do that. Please pause the video, go back and check. It's a quick exercise. Now you have all the steps. You just need to write down the key ones from the momentum balance chapter. Go back to your notes there, momentum balance chapter, or go back to the notes that are videos that are available to you, and modify the same derivation for a horizontal tube and see whether you get the same expression, except that the capital P turns out to be equal to small p, and therefore P naught, the pressure P naught minus P L can be written instead of the capital P. Please go ahead and do that and then get back. This is the way we learn to do things. You need to do it on your own. Okay. Go and do that. Take as much time as you want. You just pause the video, then come back. Okay, hopefully you did that. You derived and found that indeed for a horizontal tube, the velocity profile, you got the same. The only difference was that instead of a capital P, you have a small p here. The capital P in the case of laminar flow through a horizontal pipe became just the pressure alone without the rho g h term that is being associated with it. Okay. Let me, I think it's all coming together here. So, let me change this a little bit. Yeah, some of that got left out. That's okay. Don't worry about it. Okay. So, you checked this, you found this. Let's move forward. So, we substituted the continuity equation into the equation of motion and got this. That's simultaneous solution, right? So, we are making use of all the applicabilities one after another, same time, and so on. Now, if we substitute 6.3-5, it's the velocity profile here, right? Yeah, 6.3-5 into the energy equation that we had, and to do that, you need to differentiate this because we have a dVz, dou Vz, dou Z term, and so on. If you do that, then the energy equation becomes rho Cv hat P naught minus PL r squared by 4 mu L 1 minus r by r squared dou T dou Z equals K times 1 by r dou r dou T dou r plus dou squared T dou Z squared plus a mu dou Vz dou r the whole square. Okay. Nice complex equation. If you can solve it, it's fine. Okay. And usually we find ways of simplifying this because of the level of mathematical effort that is needed. We want to simplify it to the extent possible that represents the situation well without too much of compromises. In other words, it's a good approximation. That's what we are looking for. This is equation 6.3-6. Usually, the heat diffusion term, note that this is K on the right hand side, right? This is K times dou squared T dou Z squared. K by rho Cp you know is alpha, alpha dou squared T dou Z squared. So, it's a clear diffusion kind of a term. This is called heat diffusion. So, the heat diffusion in the Z direction is negligible compared to the convector term. Okay, the rate at which it's going to diffuse by molecular motion is going to be much less compared to the bulk flow component. All this is heat. Okay, the heat diffusion and the heat being transferred by convective motion. Therefore, this term is going to be much negligible compared to dou T dou Z term here. Okay, where it's all additive here. Therefore, we can neglect this term when they are added together and so on. Therefore, after differentiating 6.3-5 to get the last term in terms of the relevant variables, we could write this term drops out, rho CV hat Vz, this is nothing but Vz max, right? P naught minus PL R squared by 4 mu L is nothing but your Vz max. Go back to your momentum balance notes to laminar flow situation to find that out. 1 minus R by R squared, of course, dou T dou Z equals K 1 by R dou R R dou T dou R. This term, of course, we have neglected in comparison to this term, plus we had an expression for Vz, we had differentiated. If you differentiate and then substitute here, please do that and check yourself. P naught minus PL R squared by 4 mu L squared 1 by R power 4 times 4 R squared. This is what we get, you can check. Or this can be written as, this is nothing but again Vz maximum squared term here. Therefore, rho CV hat Vz maximum 1 minus R by R squared dou T dou Z equals K 1 by R dou R R dou T dou R plus mu times 4 Vz max squared R power 4 R squared. Now, viscous dissipation, the phenomenon that contributes to the last term in the RHS, which is this, right? This is coming directly from here. This is viscous dissipation, the energy term. It's important only when the velocity gradients are large. Okay, that comes from dVz dr, dou Vz dou R. So only if the velocity gradients are large would this term even be relevant. So if the velocity gradients are not large, in other words, we are imposing one more condition on our solution to get a handle on that. And then, of course, we are very aware that these are the assumptions that we have made. We need to ultimately go and check. But let me just show you what happens if you put in these to have a handle on the essence of the solution, the picture that we are looking for. If the velocity gradients are not large, then the last term mu dou Vz dou R squared can be dropped. In other words, whatever term that came from that can be dropped. If it is not, then of course you need to have that and figure out ways of solving the equation. So if you drop that, your equation just becomes this: rho CV hat Vz max 1 minus R by R squared dou T dou Z equals K 1 by R dou R R dou T dou R. This is equation 6.3-7. Under this, under one more assumption here, that the viscous dissipation is not large. Of course, you need boundary conditions to solve variation of T with Z, variation of T with R, and so on. So at R equals 0, the center line, the temperature is finite, and therefore dt dou T dou R equals 0. That you know already. Standard boundary condition by now. Equation 6.3-8. At R equals the surface, R equals R, minus K dou T dou R is the heat supply rate. Okay, this is the heat that is being supplied due to conduction, right? And therefore, at the wall, that is, it's completely through conduction. And therefore, minus K dou T dou R equals Q1. This K is that of the layer that is closest to the wall, and the K is the conductivity of that. 6.3-9 equation number. And you need a condition for Z. So at Z equals 0, this is the second order in R, first order in Z, as you can see. At Z equals 0 at the starting point, T equals T0. Okay, the entire liquid is at some T0. 6.3-10. If you substitute these and find, or let's do our usual thing, non-dimensionalize, we'll come up with a certain theta that is defined, the temperature, the non-dimensional variable corresponding to the temperature, theta equals T minus T naught divided by Q1 R by K. We are defining it like this. Equation 6.3-11. A xi variable R by R, equation 6.3-12, and let's call it psi. Okay, psi Zk divided by rho Cp hat Vz max R squared. Okay. This is a xi, this is a psi. This is equation 6.3-13. Now, we need to write this equation in terms of theta, xi and psi, and then figure out a way of solving it. Then we get t as a function of z. That is what we are looking for. If you do that, or theta as a function of psi. Okay, that is, psi is where your z happens. We are not worried about r in this case, therefore, we are looking for theta variation with psi to begin with, and then of course, you can substitute all these values to get t as a function of z. This psi, which has been defined as this zk divided by rho Cp hat Vz max R squared, it has been defined in this way, and it can be viewed as z by r mu dvz average rho k by rho mu Cp. Okay. I have just separated out the variables, grouped them together, and so on and so forth. You can go and verify this. Okay. This is zk rho Cp Vz max R squared. You could write it as this. Okay. Vz max and so on, I have replaced that with Vz average. Zk is here, the other things have come in because of that replacement. Okay. Vd by mu, and this is nothing but the inverse of the Reynolds number, and mu Cp by k is called the Prandtl number. Prandtl number is a very relevant non-dimensional number in heat transfer situations, heat transport situations, bulk, when you are looking at the transfer coefficient approach. Okay, very useful, widely used. So, k by mu rho Cp is nothing but inverse of the Prandtl number. So, you can very clearly see that it is, or we have written it as a product of non-dimensional variables that we can easily understand. For example, Reynolds number, as we saw, was the ratio of inertial forces to viscous forces in a flow, okay, and so on and so forth. The Reynolds number and Prandtl number appear in most of the forced convection situations. It's good to remember this. In terms of non-dimensional variables, the differential equation is nothing but 1 minus xi squared dou theta dou psi equals 1 by xi dou xi dou theta dou xi. Okay. So, this is what the differential equation would become if you substitute the non-dimensional variables. You can check this. If you want, you can pause the video here, go back, check. Equation 6.3-14. The boundary conditions will transform to at xi equals 0, theta equals finite, d theta d xi equals 0, that is what it means. Equation 6.3-15. At psi equals 1 minus dou theta dou xi equals 1, equation 6.3-16, and at psi equals 0, theta equals 0. Okay. Equation 6.3-17. In the limiting case of large psi, an analytical solution exists. Okay. Of course, you could solve numerically. Okay. You look at this, it is quite daunting to begin with. You can attempt numerical solution if you know how to go about numerical solutions. If not, at least for large psi, there is an analytical solution which you can get from mathematical textbooks for problems of this kind with this kind of boundary conditions. For problems of this kind, boundary conditions are for specific situations, specific constants and so on. So, the analytical solution turns out to be theta equals minus 4 psi minus xi squared plus 1 by 4 xi power 4 plus 7 by 24. So, you have theta as a function of psi, right, and of course, it is going to depend on r, and that is or xi, r by r. However, our interest is in a particular r, what is going to be the variation, or you could look at an average temperature, you could calculate an average temperature and so on. So, this is one of the ways of getting a solution for our particular situation. More importantly, this was to illustrate the case of simultaneous velocity gradient and temperature gradient, and we took the equations approach and showed you an example of simultaneously solving three different conservation equations: the equation of continuity, the equation of motion, and the equation of thermal energy. And the solution for this mathematically involved situation exists, at least for a limiting case, we know the solution. Okay? In other words, for large psi means a large distance from the entrance, we can get it as a function of psi, get it as a function of z. Okay. I think that's all that I have for you in this class, in this lecture. Yes. So let us stop here. When we come back, we would look at velocity gradient along with temperature gradient being applied to a highly widely used situation of a heat exchanger. Okay. That's a very key equipment in process industries. So we are going to look at this, and since it is process industry based and so on and so forth, we are going to use the transfer coefficient approach. The equations approach might get very messy, so we will use the transfer coefficient approach and get useful relationships for design operation. It also gives us some insights. Okay, see you in the next class. Bye.